It'll fit in. All right, so whenever you want to begin, maybe with an introduction of yourself.
Yep, and sounds fine. You can hear?
Yep. Sounds good.
Yeah. Okay. All right. So, good morning. My name's Phil Schauer, and I work in the group of Professor Curtis Burlingett, currently over at the University of Calgary. And I'd like to talk today about some work that was done by myself and two of my colleagues, Matej Bezdek and Dmitry Pogazev. And this work here is presenting our work on developing a new chromophore for the dye-sensitized solar cell. So our research within the Burlingett group is mainly oriented towards ruthenium chromophores for the dye-sensitized solar cell. And what we're looking at is trying to take the existing champion dyes, as illustrated along here, and improving them for better performance, better stability, and to actually get towards a functioning commercial device. So if we do look at the current champion ruthenium sensitizers, we see that there's a common motif of not just the dicarboxybipyridine ligand, which assists in binding to the titanium, but predominantly these isothiocyanate ligands are a strong feature in all the current champion dyes. And the problem with these is that they are actually labile ligands, so during the performance of a cell, these can actually be substituted by other components within the electrolyte. And also the problem is that they're not an easy functional group to modify. So unfortunately, the highest occupied molecular orbital of the actual complex itself resides predominantly on this ruthenium and the isothiocyanate ligands. Right, and so to actually modify this very important property of the HOMO, we can't do that with the thiocyanates. So what we've moved towards in the Burlingett group is predominantly looking at cyclometylating pyridine or cyclometylating pyridine-derived ligands, which allow us to have a stronger chelating ligand to replace this isothiocyanate, and it also allows for more flexibility in actually expanding the optical and electronic properties of the complex. And in this particular case, we've gone for a naphthalamide core, which is something that hasn't actually been developed at all in the literature. It's a novel ligand, and particularly for use within this system. And the beauty of this particular pyridyl naphthalamide core is that it allows for a very modular synthesis to tune various parts of the system. And that's allowed us to go on, as I'm about to explain, and actually explore some components of this ligand and its interactions with the rest of the dye-sensitized solar cell. So our basic modifications have been off the amine, predominantly with benzyl or phenol-derived ligands, as well as actually modifying light harvesting units onto the pendant pyridine group. And within this, we can see that through the complexes, the majority of the optical properties are actually consistent across the series, and we do have a nice strong absorption, which is of course desirable for the DSSC, absorption through the visible region, and this is an absorption that's predominantly oriented on the ruthenium metal and naphthalamide, in combination with enhanced light harvesting from our ability to include another hexylphenol bipyridine moiety. Across the series as well, the complexes have very similar electronic properties, and most importantly that even when we do have very electron-rich substituents on the naphthalamide or as another pendant ligand, we're still maintaining electronic energy levels that are suitable for the operation of the actual dye-sensitized solar cell, such that we're matching the appropriate energies for injection to the conduction band, as well as regeneration by electrolyte medium. And we were pleasantly surprised that through the series, we were able to achieve high efficiencies for actual power conversion efficiency of solar radiation. And in our case at least, these efficiencies will actually outperform the current champion N3 dyes operating under the exact same system. And with remaining modifications to the scaffold, we can actually more closely fine-tune things like the recombination processes and further modify for additional light harvesting possibilities. And that's basically where we're at the moment.
Now between the valence and conduction bands, you've got a forbidden gap. And if the gap you've got is just too wide, you'll lose your photons in a snap. Now if the gap you've got is far too narrow, you'll catch the whole darn fleet. But that won't do you any good, 'cause all you'll get is heat. Oh, solar energy, yes, solar energy. We can have our fun with the power from the sun using good old PV.